In this section, we're going to be looking at graphing with higher order polynomials. And again, I want to relate what we've done before with parabolas to what we're about to do with higher order polynomials. Looking at zeros and intercepts, looking at turning points. When we talk about parabolas, they're usually called a vertex. And we're also going to look at the leading coefficient and how that affects the behavior of the graph. In this example, we're asked to graph a function, and we're also asked to set our windows to specific numbers. So I've already typed in my equation. Now let's go to the window button. I want my x to go from -10 to +10 with a scale of 1, and it's already set like that. I want my y's to go from -100 to +100 with a scale of 10. So press enter, and then we can graph it. And I can see all of my x-intercepts and my turning points on this graph. For my second problem, I have that typed into my calculator. And since this is a multiple choice question, I want to look at my answer choices and see the windows that they have. So for my x values, they go from -5 to +5, and my y values go from -60 up to +20. And notice that on the horizontal axis, my x values go by increments of 1, and on my vertical axis, my y-axis, my scale is 10. And I see that my graph matches up with option A. And once I'm finished with this problem, I want to reset my window on my calculator to my standard window. And the quickest way to do that is zoom 6. Now, problem 3, I'm asked to graph the function, determine the interval on which the graph is increasing, and determine the interval on which the graph is decreasing. So there's my graph. It looks like a parabola almost, except for the turning point down toward the bottom is a little flatter than a parabola. So there's a quick sketch of my graph. Now, when I read a graph, I read my graph from left to right. So as I start over as far to the left as I can, and I have my cursor on my graph, and I follow along just like it's an ant following along here. It's going downhill. This is decreasing in this part of the graph. So these are the x values on which my graph is decreasing. And actually, I don't start just where my marker started here. I actually am starting out toward -infinity and then up till I get to this point right here, which is the point 0 on my x-axis. And once I get to that point, then I'm starting to increase. I'm going to highlight this in yellow. This is the section of my graph where I'm going up the hill. So it's these x values that will give me the interval on which I am increasing. So remember that when I'm looking at intervals, I'm looking for x values, and the x coordinate of this point right here, this turning point, is 0. So I am increasing from 0 to infinity, and my graph is decreasing from -infinity to 0. When you are writing where your graphs are increasing and decreasing, remember that you always use parentheses at your endpoints. And again, the definition of a turning point is where you're changing from increasing to decreasing or from decreasing to increasing. In this problem, I'm asked to approximate the real zeros and the turning points in the graph. remember that the real zeros are your x-intercepts. In other words, that is where your graph crosses the x-axis. So here, here, and here. So my real zeros are at -6, -3, and +1. My turning points are here, here, and here. So I'm going to just approximate these. I'm not going to be able to get an exact answer here. My turning point's about -5, -20. And here it looks like I'm right on the x-axis at -3, 0. And this turning point looks to be about 0, -55. And next we're going to talk about how the degree of a polynomial relates to the number of zeros, the number of x-intercepts, and the number of turning points. First of all, the number of zeros. A polynomial function of degree n has n non-distinct zeros. A polynomial function of degree n has at most n distinct zeros. So we're going to spend a little bit of time on that, looking at what that means. Okay, let's look at example 5. Here I'm given the zeros of -3, 4, 5, and 8. This function has 4 distinct zeros. All of them are different. That's what it means by distinct. Problem 6, my zeros are -2, 1, 1, and 7. You'll see that these zeros repeat. I have one listed twice. So I have 3 distinct zeros. That means 3 zeros that are different from others. Going back up to my definitions, the number of x-intercepts, a polynomial function of degree n has at most n x-intercepts, and the maximum number of turning points of a function of degree n is n-1. I think all that sounds a little bit more confusing than what it really is. Once you see how we apply these concepts, I think you're going to get comfortable with these definitions real quick. Okay, for problem 7, I have a polynomial. Degree is 5. It's the biggest exponent. The maximum number of zeros is going to be 5. It's the same as my degree. The maximum number of x-intercepts is also going to be 5. The maximum number of turning points is the degree minus 1, or n minus 1. So in this case, 5 minus 1, which is 4. So a maximum of 4 turning points. Problem 8, I have a polynomial of degree 8. The maximum number of zeros is 8. The maximum number of x-intercepts is 8. And the maximum number of turning points is 8 minus 1, which is 7. Here are the directions for the next few problems. The graph and degree of a polynomial with real coefficients f of x are given below. Determine the number of real zeros and the number of non-real zeros of each of the following. And each zero is distinct. So if I have a polynomial of degree 4, that means I'm going to have 4 zeros. The number of real zeros are my number of x-intercepts, which is at this point and this point. So I have 2 x-intercepts, so 2 real zeros. So that means I'm going to have 4 minus 2, 2 imaginary zeros. This polynomial has degree 3, so there's 3 zeros. I have 1 x-intercept, so 1 real zero, 3 minus 1, is 2, so I have 2 imaginary zeros. Now, this is the graph of a parabola. So our rules for higher order polynomials still relate to parabolas as well. Degree 2, I have 2 zeros. I do not have any x-intercepts, so that means I do not have any real zeros, so I have 2 imaginary zeros. And just as a quick reminder, when we talked about these type of problems that did not have any real zeros, we knew that the discriminant was negative. In this problem, I'm asked to determine the real zeros and the factors of the polynomial graphed below. My real zeros are my x-intercepts, -4, -1, 2, and 6. My factors are x plus 4, x plus 1, x minus 2, and x minus 6. The directions for this problem are the same to find the real zeros and factors. So pause the video and see if you can do this one on your own. So my zeros are my x-intercepts of -3, 2, and 5, and there are my factors. The directions for the next set of problems says to use a graphing calculator to approximate all the real zeros of the function and round to the nearest hundredth. So I type my equation into my calculator. I'm going to look at my graph. And I can see I have a zero that's somewhere in between like 0 and -1. It's hard to tell. So what I'm going to do is zoom in on my window. Let's say -3 for the minimum x value and +2 here. And let's go by 0.5. And let's see if that graph's a little bit easier to read. And it is. So I want to find this 0. I'm going to hit second trace, will take me to my calc button. And I want to find the 0, so that's option 2. Press enter. And notice my cursor is here flashing. And down below here, I'm asked for the left bound, so I use my arrow keys to scroll to the left of my 0, press enter, then scroll to the right of my 0, press enter. It's asking me to guess, press enter, and my 0 is approximately -0.74. There's problem B that I have typed into my calculator. I'm going to look at my graph. And I can see that my window is already set like I need it to be. So from here, I'm going to hit second trace. I want to find my 0. Scroll over to the left of the 0. Press enter. My right bound. Press enter. And then enter one more time. And I get my 0 of -1.5. For this next problem, I've gone back to my standard window real quick so I could see the whole graph a little bit easier. My exponents in my equation are both even, so my graph is going to be symmetric about the y-axis. So if I find one of my zeros, then I know that I can just take the opposite of that to find my other zeros. So let me give you a second to pause the video and see if you can do that on your own. Hey, if you found the 0 that's toward the left of your graph, it's -1.03, and that means your other 0 is going to be +1.03. Earlier in the course, we were given functions like this and asked to find the zeros and their multiplicities. So we set each of the factors equal to 0 and solved. So those were my zeros. And the multiplicities were the exponents. It's how many times that factor occurs. So here my multiplicity is 3, and -1 has a multiplicity of 5. What we're going to do next is to see how multiplicities relates to graphs. Let's look at an example. Let's say I have a 0 at 2. If my graph goes through the point 2, then I know that that multiplicity is odd. Right? The multiplicity is either 1, 3, 5, 7, something like that. Let's look at an example over here. Let's look at the 0 of -3. If my graph touches this at -3 and then bounces back off, then the multiplicity here is even. The multiplicity is either 2, 4, 6, 8. So you need to be able to tell when a 0 has an odd multiplicity or an even multiplicity. The directions here say to determine the real zeros of the graph below and determine if their multiplicities are odd or even. My real zeros are my x-intercepts. So -5, 1, and 6. -5 has a multiplicity that is odd because it goes through my x-axis. 1 has a multiplicity that is even because my graph touches at that point and then sort of bounces back off. I have another 0 at 6, and the multiplicity there is odd. The directions here are the same. Determine the real zeros of the graph below and determine if their multiplicities are odd or even. Let you pause the video and try to do this one on your own. And there are your answers. Problem 17. Which of the following could be the equation of the graph shown? I want you to think about all of the things that we've talked about with degrees and turning points and zeros and multiplicities, and see if you can figure this one out on your own without using your graphing calculator. Okay, so let's talk about why this first option could not be the correct answer. I know that this is a quadratic, degree 2, so this is a parabola. The leading coefficient is positive, so I know that this is a parabola that opens up. Next, I want to look at the x-intercepts. This x-intercept has a multiplicity that is even. The smallest even number this could be is 2. This multiplicity is odd. This multiplicity is odd. The smallest this could be is 1, and the smallest this number could be is 1. So when you add those together, there's a total of 4 zeros. There's a total of 4 zeros, so I have to have at least degree 4. So that's my answer.